Okie doke. Now we're going to move on to chapter 8, which is the chapter on linear momentum. It takes into account both elastic and non-elastic collisions, which we'll discuss a little bit more detail once we get to that point. The first problem we're going to do is problem number 1. Calculate the momentum of a 200 kilogram elephant charging at a speed of 7.5 meters per second. Okay, so we have momentum is equal to mass times velocity. In this case, we have a 2,000 kilogram elephant running at 7.5 meters per second. And that equals 1.5 times 10 to the fourth kilogram meters. The second part of this problem states, compare the elephant's momentum with the momentum of a 0.04 kilogram tranquilizer dart fired at a speed of 600 meters per second. Same formula, 0.0400 fired at 600 meters per second, and that's going to equal 24 kilogram meters. Now, if we divide one of these, if we divide this by this, we get 625 to 1. So that's the elephant's momentum is 625 times as high as the momentum of a dart that's fired. At what momentum, what is the momentum of a 90 kilogram hunter running at 47.4 meters per second after missing the elephant? So he fires the dart, misses the elephant, and again, same formula. It's 90.0 kilograms times 7.4, and in this case, it's going to equal 666 kilogram meters. Very straightforward. The next problem is problem number 4. Problem number 4 states, what is the momentum of a garbage truck that is 1.2 times 10 to the fourth kilograms and is moving at 10 meters per second? Same formula as up here, 1.4 times 10 to the fourth kilograms at 10.0 meters per second. It's going to be 1.2 times 10 to the fifth kilogram meters. At what speed would a 8 kilogram trash can have to have the same momentum as the truck? So if we put this equal to an 8 kilogram trash can times a certain velocity, so the velocity is going to equal this 1.2 times 10 to the fifth divided by 8, which is going to equal 1.5 times 10 to the fourth meters per second squared. The next problem is problem number 8. And now with problem number 8, we're starting to move into something called impulse. Impulse is defined as the force times the time at which the force is applied. And it turns out that this impulse is equal to the momentum that an object has. So Ft, impulse, is equal to momentum. And the first problem is problem number 8. A car moving at 10 meters per second crashes into a tree and stops at 0.26 seconds. So t is equal to 0.26 seconds. The car, its velocity is 10 meters per second. And it says calculate the force on the seatbelt exerted on a passenger if his mass is 70 kilograms. Okay, so the mv is equal to Ft. So the force is going to equal mv divided by t, which is going to be 70 times 10 divided by 0.26. And if you do the math here, you get 2,700 newtons. Number 10, a professional boxer hits his opponent with a 1,000 Newton horizontal blow that lasts 0.15 seconds. So the force here is 1,000 newtons, and it lasts, the time is equal to 0.150 seconds. The question is, calculate the impulse imparted by the blow. Well, that's just Ft, which is just 1,000 times 0.150, which is going to be equal 150 newtons per second. Newton seconds, excuse me, not newtons per second, Newton seconds. What is the opponent's final velocity if his mass is 105 and he is motionless in midair when he's struck near his center of mass? So if we put this impulse equal to his momentum, it's asking what v is. So we have 150 divided by his mass, and his mass was 105. So his velocity is going to equal 1.4 meters per second. Now it changes and says, assume instead that instead of striking him in his center of mass, you strike his head, and his head has a 10 kilogram mass. And you assume that this force does not transfer to his body, but only to his head. And so now you have the same force, but it's now transferred to a 10 kilogram head. So the velocity now becomes 15 meters per second instead of 1.4 meters per second. And it says, discuss the implications of your answers for parts B and C. Well, what this shows you is that if you hit somebody in their stomach, the velocity that their whole body will take on is a fairly small number. If you hit them in the head, the velocity that their head takes under is 10 times the velocity that their body assumed. And that's why when you see somebody get hit in the head, their head snaps back. It's because you assume that the force is about the same, so the impulse is about the same, but now you're hitting a much smaller object when you're hitting their head, and that causes this velocity to be much greater. And that's why people get knocked out when they get hit in the head. It's because of the velocity that their head has. Number 14, military rifles have a mechanism to reduce the recoil forces of the gun on the person firing it. An internal part recoils over a relatively is the key word there, large distance and is stopped by a damping mechanism of the gun. The larger the distance reduces the average force needed to stop this internal part. So A, calculate the recoil velocity of a 1 kilogram plunger that is directly interacts with a bullet of 0.02 kilograms fired at 600 meters per second. So we have mv for the bullet is equal to mv for the stopper, or whatever they've called it. They called it a plunger, and the plunger is 1 kilogram. So the velocity of the plunger is going to equal the mass of the bullet, which is 0.02 times 600 divided by 1. And so that's going to equal 12 meters per second. So without the dampening mechanism, the recoil of the gun is 12 meters per second. Now the second part of the problem states, if this part is stopped over a distance of 20 centimeters, what is the average force exerted upon it by the gun? So what we have to do here is look at the initial kinetic energy minus the final kinetic energy, and the final kinetic energy is going to be 0. It's actually, I should write this the other way around. The final kinetic energy minus the initial kinetic energy is only going to equal the work done by the plunger, which can be written as force times distance. Now this is 0 because the recoil is stopping, okay? So what you end up is minus 1/2 mv squared divided by d, well, let's do it this way, is equal to fd. And so that means that the force, if we solve this for the force, that's going to equal mv squared over 2d. And we found that this was the velocity. The mass is 1 kilogram. The velocity is 12, so we square that. We do that over 20 centimeters, or 2/10 of a meter, times 2. And so the average force is going to be minus 360 newtons. And it's minus because it's stopping. It's exerting this to stop it. Part C says, compare this to the force exerted on the gun if the bullet is accelerated to its velocity in 10 milliseconds. So F again is question mark. We don't know what the force is. The T is 10 milliseconds, which is 0.01 seconds. 1 millisecond is 1,000th of a second, so 10 milliseconds is 1/100th of a second. We know the mass of the bullet is 0.02 and the velocity is 600. So Ft is equal to mv, so F is equal to mv divided by T. So that's going to equal 0.02 times 600 divided by 0.01. So this is 12 divided by that is going to be 1,200 newtons. And so the positive force to get this going is 1,200 newtons. The negative to stop it is 360. If you divide this into this, you get 0.3 is the relationship between those two forces. One more problem before we change the go to another video. We'll do one more, and the last one we're going to do is number 23. And with number 23, we are now moving into the idea of conservation of momentum. And one thing I'll say is you need to set 2 time periods, the time before there's a collision and the time that there's after a collision. And the 2 time periods, the momentum has to be equal between those 2 time periods. That's what is meant by conservation of momentum. The other thing is you, in order to do these properly, you have to have a a standard saying, for example, that left to right motion on your paper, for example, is always going to be positive, and right to left motion on your paper is always going to be negative. And that way, if you do that, you can keep track of objects that are either traveling in the same direction versus objects that collide and are traveling in opposite directions. So let's look at number 23. Train cars are coupled together by being bumped into one another. That means that they generally are traveling in opposite directions. Suppose 2 loaded train cars are moving toward one another, the first having a mass of 150,000 kilograms. So that's 1.5 times 10 to the 5th kilograms. And the second one, and it's traveling, let's just say in this direction, at 0.3 meters per second. And the second one is they're bumped into each other, means they are run toward each other and collide. The second one has a mass of 110,000 kilograms, and it's traveling at a velocity, and it says minus 120. So it tells you that they're traveling in opposite directions. What is their final velocity? Well, you have a momentum here. This is before their collision. So it's mv plus mv here, which will be 1.5 times 10 to the fifth times 0.3 plus 1.1 times 10 to the fifth times 0.12. And that's before their collision. Now, the way the problem stated, the assumption here is that after they collide, you have two cars that are coupled together, so they're essentially one mass. So you have add these two masses together, you have 2.6 times 10 to the fifth kilograms. So this is going to have to equal the mass times the velocity of this single object. So if you take this and divide it by 2.6 times 10 to the fifth, that's going to give you, that's moving this to this side, that will give you the velocity. So if you do the math here, you end up with 0.12 times, meters per second. And because it's positive, that means it's traveling from left to right. So doing the math out here, you have 3 times that's 4.5 times 10 to the fourth plus, and that's 1.21 plus a minus 1.21 times 10 to the fourth. You put those together, you end up with 3.3 or 29 times 10 to the fourth over 2.6 times 10 to the fifth. And you can see if you divide these two numbers into each other, you can get something like that.